Hello everyone. So welcome back. So today I will be solving one another medium level problem on LeetCode. It's called unique paths. So let's see what this problem says. So a robot is located at the top left corner of M cross N grid marked as start in the diagram below. The robot can only move either downwards and rightwards from any point from at any point in the time. Okay. So the robot is trying to reach from bottom right corner to the from the top to bottom right corner. So we have to count how many possible unique paths can there be. Okay, so let's understand this problem now. So given above is a 7 cross 3 grid. The robot is standing over here. This is called as start and this is called as finish. So the robot has to reach here. So there can be many paths, like it is only allowed for the robot to move right direction and downwards. So it can go like this is a path, like right, then down. So this is a valid path. Or it can go like down, right. So this is also a valid path. And also there can be many multiple valid paths, like right down, right down, so on. Okay, so there can be many valid paths. So we have to find out how many exactly unique paths are there uh, possible in this problem. So we are given with m and n, and the answer is over here is 3. Let's see how the answer is 3. So there can be only 3 unique paths. One is right down, and right and down right. So how is these things are working? So let me go to the whiteboard and draw something to make you guys understand a little bit better. So here you can see that we have drawn a grid of 3 cross 2. Here n is 2 and m is 3, and the grid looks like this. So here is the starting point and E is the ending point. So there are only 3 moves possible, 3 unique moves. And let's see how is that even valid. Like, first of all, we have to see that only right, which is like this, and only down, which is like this, these 2 moves are allowed. So first of all, right down. So let me change the color and show you how is right down. So first move right, then again right, then down. So this is one unique move. Then there is right down right. So first right is drawn over here already, then down, then right. So this is another move. And lastly, that is down right. So that will be down one move, and right, and again right. So these are the 3 moves which are possible using this 3 cross 2 grid. So let us see how to approach this problem. So let me clear the screen, and let me tell you one thing, that is, let's say, let me just break this bigger problem into smaller sub problems. So let's say, first of all, when m is 1, or let's say n is 1. So if m or n is 1, so how the grid is going to look like? So let's say m is 1, then the grid will look like something like this. And no matter value of n can be anything, so the grid will look like this. And if n is 1, then the grid will look like this. And here also, no matter how much value of m is there, the basically there will be one straight line. So now we have to understand one thing over here. If either of m or n, any of the values is 1, we can see there is only one unique path from start to end, like this straight line only, because it is only going what, down and down. Here also right and right, only one possible unique path possible. So this becomes our base case. So whenever m is there and n is there and any one of them is 1, we see there is only one path possible. So for this case, the answer would be only one. So let's see another case. So let me clear the screen and draw something. So let us think now, the grid is 2 cross 2. So grid is like this, 2 cross 2, start and end. So what are the possible ways to reach from start to end? So the possibilities are only right, and down, or down and right. So there are only two possibilities. One is right down, another is down right. So whatever the possibilities are there, from here to here, we have to take the minimum of them. Sorry, we have to take summation of them, because we have to find total unique. So we have to find total unique. So here is one path and here is one another path. So the total path is right down plus down right. So I hope you are understanding, right? We are, from the smaller problems, we are building up to solving the bigger problem. So we are going to use dynamic programming over here. Before dynamic programming, I will be solving this problem using three of the approaches. First, we will be solving it using recursion, then we will be memoizing it, and then ultimately we will see how to solve it using top down DP. So this is the base of the problem. We have to understand this, that we will be taking the summation of, let's say, if the grid is like this, and we have to reach from here to here, we will take all possible paths. Like, once we are starting from here, another starting from here, then we will explore all its possibilities. Like, then it can be here and here, then from here it is here, then here also we will explore all the possibilities, and we will sum up all the possibilities, and we will get the answer. So now let's see how to do this in the code. So before that, let me tell you one thing, how our recursive program structure will look. So let's say our function name is fun, and it will take two parameters, one is m, one is n. So what we have seen from this example, where it was 2 cross 2, we see that one possibility is, if this is n, and this is m, like this axis is m and this axis is n. So first we increment n and check how many unique paths are there. Then we do what? We will again make n as previous, and we will increment m and check. So this is a bit tricky to understand, but I hope whenever I will be coding it, you can understand this. So basically what we will do is, we will think of this problem like, we don't have to reach from start to end, we will do the opposite, we will reach from end to start. So they are basically the same problem, right? So for n to start, we will first decrement the n value and keep the m same, and we will check how many paths are possible. So let's say the path is p1, then we will decrement n and keep the m as same, then we will get path 2, and the summation of these two paths will be our answer. So this is our approach. So let's go to the now code editor, and let's see how we can solve this. So this recursion call will now make two recursion calls. One is function of m minus 1 n, and another is function of m comma n minus 1. So these two will be our subroutines. So now we see these two calls will be having many similar subproblems. So we will also see how to use memoization and dynamic programming over here. So this is the base of our problem, and now let's see how we can solve it.
Whatever I have explained in the whiteboard, if you had any doubt, I hope after seeing the code, it will be more clear for you. So let me just start writing the code. For this code, we will need one recursive function. Okay. So for recursive function, let's say call the recursive function as unique paths REC, or unique paths recursion. So self dot unique paths REC, and we will pass m comma n, and whatever the value computed from this function, we will just simply return it. So this is our task done for this function. So now we have to define this magical recursive function over on the top. So let's just define it. So first of all, let me name that recursive function, and the first argument is obviously self, so it is there, and m and n. So first task is writing the base case. So let me tell you one thing. Whenever we are trying to write the base case of any recursive problem, let us just think about the smallest possible input, or smallest possible valid input for this problem. So what is the smallest possible value that is valid for this problem? So obviously m and n both cannot be negative, right? because they are indicating the number of cells in a grid. So number of cells in a grid cannot be negative. So that's why the smallest possible value which is valid here is 0. So let's say if m is equal to 0 and n is equals to 0. So let's say if both of them are 0, so that means the grid doesn't exist at all. So that means our possible unique paths would be what? Obviously 0. So this is how we are thinking of the base conditions. You can see from my thinking, right? So now we will write another base condition which I have just told in the whiteboard explanation. So now let's say if any one of the value is 1, like if m is equal to 1 or n is equal to 1. So this means what? That the grid is only a straight line, either horizontally, either vertically. So the only unique path will be 1, right? So that means we will return simply 1, or else I have told that we will take the sum of two recursive calls. One is where we will be decrementing m, another is and keeping n as same, and another is decrementing n and keeping m as same. So basically these two recursive call will do what? It will first go to the upper row and check all its possibilities, and another call will do what? It will go to the left and check its all possibilities. So we are here given as down and right. So why we are just doing the opposite here, as I have said, left and upwards? Because as I have also told that we are not considering from going to start to end. We are doing the opposite. We are considering from end to start. So they are basically the same. So if we are going from end to start, so the moves will be also flipped. Like right side will be becoming left side and downwards will be becoming upwards. So we can do also like from start to end, but this way it is more intuitive. So that's why I'm teaching this way. So now return. So let me just copy this function name once again. Self dot this function name, and first m minus 1. So this means we are going left side and keeping n same, plus self dot. Now we have to go to upwards, so keeping m same and going upwards. So this is pretty much it for our function. So let's run it. So we can see it's accepted, but the problem here lies that this recursive code having many what you say is many sub problems which are overlapping. Like whenever we're calling, let's say we are calling this for 3 2. So for 3 2 this function will be calling 2, because m is 3, so 3 minus 1 is 2, 2 comma 2, and another one is this, so this will call 3 comma 2. So again this 2 2 will be calling 2 2 will be calling what? 1 comma 2, and also 2 comma 1. So same way this will be also calling two functions, 2 comma 2, and here we can see this overlapping sub problems. We already solved 2 comma 2, but this function is also again calling 2 comma 2. So we have to fix that. So if we submit this code, whatever it is here right now, it will give time limit exceeded. So let's do that for verifying once. So if we submitted it, we will possibly see time limit exceeded. So it will take some time because it's computing. So while it is computing, let me also tell you one thing. So here you can see that it's giving time limit exceeded. So we have to use dynamic programming or memoization over here. So the time complexity of this recursive code is 2 to the power n, because it is having the branching factor 2, because one function is calling two separate functions. So the branching factor is 2. Here you can clearly see this kind of similar to Fibonacci series recursive program. You can see one function is calling two functions over here, and we are taking the summation, so it's 2 to the power n or exponential. So how to fix that? So first I will show you how to write dynamic programming codes using memoization. So for memoization we will need one array or any hash table also to store the sub problems. So we will take one memo array, or rather memo hash table, which is dictionary over here in Python. So let's just take it, memo. So we have to pass in each function called memo. So after passing, this is simple variation of recursion, and we will see it will do a huge optimization. So whenever we are at the base case, we know the solution. So what we will do is, in the memo, we will put as key is str of m, plus we will give one space and put str of. I will also explain how this is working. This video is going to be a little longer than usual, but you will get a clear understanding of how dynamic programming and memoization and top-down DP works. So bear with me and you will understand a lot of things. So here we will do what? We will be storing this 0 corresponding to this key over in the memo table, and we will then simply return. Here also we will do the same thing. We will take this memo, and here instead of 0 we will be storing 1 and then return. Now we have to check whenever we are making any function call, if that function call's result is already in our memo hash table, then we will just directly return. So how to check? So if str of m plus str of n in memo, so that means what? This is there in our memo table. So then we will do a simple return of this value, return this, or else we will do what? We will store first in str of m minus 1 and n. Here we will store the function value of this here, and again let me just copy this whole thing so that I don't have to type so much. And here, so here we can see the n will be same and n minus 1. So here I will put n minus 1 and here m. So after storing, the result will be what? The result will be the summation of these two values. So we will take these two values and we will sum it up. Control C, Control V, and plus this value. Control C, Control V. So this is our memoization version of the DP. So let us just run it and see if it gets accepted this time or not. So okay, this is missing one argument because we have to pass the memo also. Memo. Okay, now this should work. So we are getting another error over here in the return type. Which says what? Okay, so I have made small mistake over here. So we are just returning nothing. So we have to return this value also now, because we are storing it, but we are not returning it. So how can the next function calls will get the value, right? So we have to return those values also. Now it should work, I hope. So sorry for those small mistakes. So sorry. So now we can see it's accepted. So now if we submit it, we can see it will get accepted eventually. Previously it was giving time limit exceeded, but now we can see it get accepted. So this memoization increased our time complexity from being exponential to time complexity which is getting accepted. So let us just analyze the time complexity now. So for this, the time complexity is basically m into n, because we are doing like all possibilities from where n minus 1 is there and all possibilities where n minus 1 is there. So from the 2 to the power n or exponential time complexity, we are reducing it to big O of m into n, so which is quadratic time complexity. So this is a huge optimization over exponential time complexity. And if you talk, if we have to talk about the space complexity, just because we are using this memo hash table, the space complexity will be over here is of order of n. So this was the memoization solution of this problem. So now we will do what? We will do the top-down DP. So this is also another technique of DP. DP can be done using two ways. One is memoization, another is top-down. So in this one long video, I will be teaching all the processes. Okay. So let's do and modify our current code to make it top-down DP. So we don't need any recursive function over here. because one another thing uh, which is good in top down but which is not good in memoization, that is in top down we don't have to like call the recursive function. Actually we will use only a 2D matrix for solving it, so the recursion call overhead is not present here. So that is one good thing over in top down DP. So for top down DP we will use we will use one 2D matrix. So let's just make this 2D matrix. So this 2D matrix will consist of all the zeros first, sorry, all the ones, and I will tell why it is all the ones. For I in range, so for I in range over here it is n plus 1, so here also we have to put 1 for I in, sorry, for underscore in range m plus 1. So we are making this grid over here. So let me just first print this grid to see if it's even printed or not, or I have made some mistakes again. Okay, no, so it's made. Here you can see it's we have just made one extra column, and why is that I will also explain. So if it's 3 cross 2, there is 4 cross 3. Okay, so perfect. So now we are taking one extra column because first, as I have said, if the values of m or n is 1, then all the values or all the possibilities are 1. So that's why the first row and first column will always be filled with ones. Okay, so we have to start traversing the matrix from the next one, sorry, the next column or next row. So for I in range, I will be starting it from 1 obviously, comma m, and for I in range it will be 1 comma n. So now this memo of I and j will be the summation of, as we have done in the recursive code, we will first minus 1 from m and keep the n same, and we will minus 1 from n and keep the n same. So it will be of memo of m minus 1 n plus, sorry, not n, j, I and j, I minus 1 j, and plus memo of j minus 1, sorry, yes, j minus 1, and I will be over here, sorry, yeah, I'm making some mistakes because this is going to be a very long video because I'm explaining so many things. So after solving this, we hopefully have our answer over in the last cell of our grid. So we have to now return simply the last cell of our grid. So last cell will be return memo of n minus 1 and m minus 1. So this is the last cell and we are returning this. So let's just run our code and check if we are getting some errors or not. So we are getting, oh, because it will be G obviously. I'm making so many mistakes while typing. And let me see why this is coming. So as the video was going so long, so that's why I've just debugged my code and found out some errors. So these will not be m plus 1 and n plus 1 because obviously the index are starting from 0, so we don't have to consider like it is starting from 1. So I was thinking that index was starting from 1, that's why I've taken one extra cell, so that is not needed. So that's why I've changed it to mn, and here also we have written those values, I mean, in wrong order. So here I have written m and here n, so it would be the opposite way because the n is number of rows and m is columns, and rest of the code is same. So now it is hopefully working. So I have not submitted it yet, but I think it's working. Okay, so it's here running for this test case. So now let's run this code, the top down DP approach. So here also again we can see the top down DP is also working, and here if we just see the times also, the top down DP is a little bit faster than this memoization. So now let me just also tell what is the time complexity and space complexity for this top-down approach also. So here we can obviously see we are using one 2D matrix, so that's why the space complexity will be obviously order of m into n, and the time complexity is also order of m into n. So apart from the space complexity, the memoization and the top-down DP is almost similar, but according to the time, the top-down DP is slightly better. And I have also shown how this DP approach is mainly laid upon the recursion. We are just modifying the recursive solution to getting this dynamic programming solution. So first we have to understand the dynamic programming solution pretty well, the exponential one. So this is a very elaborated video on dynamic programming and recursion. So thank you for watching. Hope you liked it.